Good evening. Hope you're having a going to solve questions on control system class. If you want the questions, you have to go to the description box. You go there. It will send you to Go Drive and okay. Good evening, ladies and gentlemen. Okay, so we are having a good evening. This evening, we are going to solve questions on control systems. I'm Aggrey Kwesi-Kwah. Then, if you want the questions, check the description box. There's a link which will send you to Google Drive. There you can download the questions that you are going to do this evening. So yes, I think we can begin. All right. So we are going to solve the 2018-2019 questions. These are questions from Dr. Koko himself. So I'm not saying the exact questions will come. I mean, he doesn't really repeat questions. We are hoping similar questions will come. So I think we can start. The first question. The characteristic equation governing the behavior of a linear time invariant system is shown below. All right, so we have L of S being equal to S to the 5 plus 2s to the 4 plus 5 s cubed plus 14 s squared plus 4s plus 24. Okay, so we are supposed to use the Routh-Hurwitz criteria to determine the pole distribution in the S plane. That is, we are supposed to find the number of planes, number of poles in the right, left, and on the imaginary axis. So as you already know, we have to get a table. So the first column you have the powers of x. Write it in descending order from the highest. So we have x to the 5, x to the 4, x to 3, x squared, x to the 1, then x0. Okay. Then for the highest, we start from the for the characteristic equation, you start with the highest coefficient, so which is 1. You skip the next one, then go to the because the first one has an odd power, you use only odd powers for the first horizontal or the first row. So you have 1, 5, 4. And for the second row, you use even powers. So you have 2 here, have 14, and you have 24. All right. So the third row, you know you are supposed to do determinants. So you are supposed to do a negative of, you always use this rule. This sorry, the first column will always be this. It doesn't change. You are supposed to do negative determinant. So it will be negative determinant using this row and this first column and then this second column. So you do normal determinants, then you find the negative of that. Because of that, we don't want to do the normal determinants, we do the other way. So we take this one as a principal diagonal. So you do 2 by 5, which is 10, minus 14, which will be negative 4, divided by the first number in the second row, which is 2. That'll be your input here. Then for the second number in the row, you move on to the next column. I said the first column will always be this. So the next column will be 4 and 24. So that means for your first row, the number is negative 2. Right. So using this row, this column, and this column, do 2 by 4 is 8 minus 24. That gives negative 16. Divide by 2, you have a negative 8 here. And the next column has zeros, so definitely here will be a 0. Right. So you go to the next row, you repeat the process. So here will be, and to make your work simpler, you can decide to multiply row 3 by 1 over 2. Make your work simpler, but you can leave it like that too. So let's leave it like that. So for the next row, you do negative 2 by 14, which will be negative 28, minus negative 16, which will be negative 28 plus 16. That will give you a negative 12. Divide by negative 2, you get a positive 6. Okay. All right. Then the next number here will be negative 2 by 24. 2 by 0 will be 0. So negative 2 by 24 over negative 2. You have your 24 here. Definitely here will be 0. Now for the next row, okay, that will be for s to the power 1. All right, so you have 6 by negative 8 minus 2 by 24. So you have negative 48 plus 48. So here will be a 0. Here will also be a 0. And here will be a 0. Now we have a row of zeros. Now this is a special case in Routh-Hurwitz criterion. So what you do is that you take the row before the row of zeros, which is this row, and you get, which is this row. Then you get an equation from here. So the equation goes like this. Since this is the row for s squared, right? So if this is s squared, this is s to the 1, this is s to the 0, this is, then you are done. That means your 6 will have an s squared plus, you have a 0s, this 0, right? Plus, then you have a 24. This should be equal to, all right. So this is your characteristic equation you got here. So from your row of zeros, right, let's continue. So here you get a 6s squared plus 24. This is your characteristic equation. Now from here, you already have your s squared. That means what you actually need is your s to the power 1. So to get an s to the power 1 from here, what you have to do is you differentiate your characteristic equation. So you find the p of s, which will give you a 12s, the 1. So what you have to do is that you have to replace this your 0 with a 12. Like I said, this has the s squared, this has the s to the 1. So the one has the s to the power 1, you replace it with 12. And then you continue your Routh-Hurwitz criterion the same way you do it. So from here, you do 12 by 24 minus 6 times 0, which should be the same divided by 12. So here will be a 24. And when you get this, you are done solving the question. And now all you have to do is to, now the question is, you have to find the number of poles in the right half plane, left half plane, and on the imaginary axis. All right. So this is our first row, first column, sorry. So we have from positive to positive. Positive to positive means that we have 1 on the left half plane. Then we have from positive to negative. Since there's a sign change, we have 1 on the right half plane. Now there's another negative to positive. So you have another 1 on the right half plane. Right. Now from here to here, this is where we got our characteristic equation to continue the solution, which means that that generates a whole new answers from here. So what you do is that from here to here, you have from positive to positive, that's 1. Then from positive to positive, another 1. So you have 2 here. But there was no sign change, and this came from solving using special cases. The solution is on the imaginary axis. So we have 2 on the imaginary axis. Your final answer will be 2 on the right half plane, 1 on the left half plane, and 2 on the imaginary axis. So the next question is to discuss the stability. Now from the moment you get something on the right half plane, it tells you that it's not stable. So you're to discuss, you know what to write. Next question. Right. A second order system has the transfer function g of s equals what we have here. And I'm supposed to find these terms. All right. So the first thing you have to do is that if you look at the equation, it wasn't given to you in the standard form, because in the standard form, the s doesn't have a coefficient. So let me rewrite the question. I have 4s squared plus 2.8s plus 16. Just write it in standard form, so it becomes 1 over 4 over s squared plus 0.7s plus 4. How do you get here? All you have to do is to factor or divide the numerator and denominator by 4, so that the s squared will be left standing alone. If you have that, then you have it in your standard form. So from here, you can say that our omega n squared, or our natural frequency squared, is equal to 4, which implies that our natural frequency is 2. We don't work with negatives here, so we take the positive part, which is 2. Now our damping ratio, please adding the sign, our damping ratio is supposed to be 0.7 over 2 omega n, which will be 0.35 over 2, over 0.175. Now when we have this, then we can move on to solve our question. So the first one is to find the rise time. Since this is an underdown system, you can see that our rise time is from 0 to 100%. The time taken to rise from 0 to 100%. If we use that definition, then our formula for rise time will become pi minus pi all over omega d. And omega d is the same as pi minus phi over omega n square root of 1 minus theta squared. Now what is phi? We know that cos phi is equal to zeta. That means our phi is cos inverse of theta. Then from here, but we have to divide by 180 and multiply by pi, because we need our answer in radians. We need our answer in radians because the pi is the same as 180 in radians. But please don't use degrees to solve it. If you use degrees, you'll get a different answer. So please work in radians. Yes. All right. So here will be pi minus, right? If we change the theta to radians, we will get 1.39. Let me leave it like that. All over omega n is 2 square root of 1 minus 0.175 squared. And by computing this, we get our rise time as 0.8895 seconds. All right, so that's rise time. The next question is to find settling time. Now, since they didn't give a specific range, we have to use the definition that we normally use in class, which is 2%. So for settling time, it's the time taken for the transient response to the magnitude of the transient response to get to a certain state and stay within 2% of that state. So what you have to do is that you take the magnitude from your, so you see when you have a second order system, your your response is given by 1 minus e to the negative zeta omega nt into cos omega d plus zeta over square root of 1 minus zeta squared sine omega d. Now when you try to simplify this, you get 1 minus e to the negative zeta omega nt over square root of 1 minus zeta squared sine omega t plus phi. That's when you try to simplify this, where phi is cos inverse of theta. That's phi. This is your simplification. So for settling time, you take this amplitude here, is e to the negative zeta omega n plus square root of 1 minus zeta squared will equal to the percentage range they gave, which we are using 0.02 here. As I'm simplifying this is our settling time, the t here. Our t of s will be giving us negative length of 0.02 square root of 1 minus zeta squared all over zeta omega n. Now if we put in the values, we have negative length of 0.02 square root of 1 minus 0.175 squared all over 0.175 times 2. The answer from my consultant gave me was 11.22 seconds. All right, so that's it for settling time. All right, maximum overshoot. We have our percentage overshoots. So percentage overshoot is the percentage by, or the how much the first 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 peak exceeds the final value, or it's like you're finding your peak value from your response. The percentage exceeds the final value itself. That's your percentage overshoot. Now this is given by, I don't want to go to um the proof, so I'll just write the formula here. As we go to the proof, now I'll skip. There's no time. Square root of 1 minus zeta squared times 100%. So this is why we say that the percentage overshoot is a function of the damping ratio. So if you look at your S plot, which is sigma, a plot of j omega per sigma, so the peak overshoot is just a function of zeta. So wherever your damping ratio is constant, that means your peak, or wherever your peak overshoot is constant, or wherever your damping ratio is constant, that means your peak overshoot too is constant. So this line, that's the diagonal lines on your S plot or your S, however you call it, is here. You have percentage overshoot being constant there. All right. So all you have to do is plug in the values 0.175 pi by square root of 1 minus 0.175 squared times 100. And that will give you around 57.2%. All right. All right. Our next question is to find the peak time. All right. The next question is to find peak time. For peak time, P peak given as pi over omega d, which is pi over omega n square root of 1 minus zeta squared. All you have to do is just put in the values to get your answer. All right. And the final question is the damp natural frequency of oscillation. That is the omega d we've been using throughout. So you already know the value before you even get here. So yes. Next question. The output response of a plant is given by y of t. Find the transfer function of the plant. Use the, okay, so your y of t. Please, this one is a little troublesome, so I will take my time. All right. So our question is 2t plus e to the power minus 8t plus u of t minus 3 sine 10t. All this by u of t is equal to y of t. So for our output, okay, so we are finding the output response. So we are finding y of s. So y of s is given by, now for t, you know from your tables, t is given by n factorial. So t to the power n is given as n factorial over x to the power n plus 1. Now t is 1, so you just get 1 over s to the power 1 plus 1. Plus for exponentials, you have 1 over s plus a. So this will give you 1 over s plus 8. Now this is the interesting part. So now what you this is the time shifting property of Laplace transform. So what happens is that if you have, if you have an x of t and you find a Laplace transform, you get an x of s. Now if you shift your time like this, you get an e to the power negative st naught x of s. This is what you're supposed to get. So using this principle, we are going to solve this question. But to solve this, you have to make sure that everything this is multiplying will also have a t minus 3, which means that this u of t minus 3 will be multiplying a sine of 10. So the 10 you change it to t minus 3 plus 3. That's what happens. So you've just added and subtracted, so you've not really done anything to it. So now from here, this part, everyone knows, so we can take this part out and continue with just this part. Now we have a u of t minus 3 multiplying. Now we are going to expand this. So we'll take this as 1 and we'll use the expansion for sine a plus b, which is sine a cos b plus cos a sine b. So this will give us sine of t minus 3 cos 3 plus cos of t minus 3 sine 3. All right. Then by simplifying, you have u of t minus 3 multiplying. Now cos 3 is 0.998. So let's take it as 1. So you have a sine of t minus 3 plus our sine 3 is 0.05 cos of t minus 3. All right. Now by expanding, we have u of t minus 3 sine of t minus 3 plus 0.05 u of t minus 3 cos of t minus 3. All right. So now because this is the same as this, all I have to do is write an e to the power, what is here? Negative 3s. And after doing this, you are done. You just have to write the expansion for sine. And the sine, sorry, there's a 10 that I left out. I'm sorry. This is supposed to be a this is supposed to be a 10 multiplying this whole thing. So please forgive me, I left the 10 out. So let's take it as this 10 was in there and just continue. So let's take it as this 10 was in there and continue. The only thing I've left out is the scalar multiple. So let's take it as this 10 was in there so that we don't have to rewrite everything. So now when we get here, we just have to write expansion for sine. So since I've cancelled the 10, that means that initially it was just a sine t. You know that if you have a you know that if you have a sine at and you find a Laplace transform, it will give a over s squared plus a squared. Now since we cancel the 10, we just have a sine t. So sine t will be giving us 1 over s squared plus 1. And you're done with that part. Plus 0.05 times. So here you have a e to the power negative 3s. I have a cos. Now since the sine is t, then your cos will be t. We have s over s squared plus 1. Please, I'm reminding you that we cancelled the 10t from our work, so it was a mistake. I'm not saying that's what you do when you're solving the question. It was a mistake. So please, if you are doing it yourself, you should correct it. All right. So finally, you will get e to the negative 3s multiplying 1 over s squared plus 1 plus 0.05 s over s squared plus 1. Then you add your 2 over s squared plus your 1 over s plus 8. And this will be your final answer for that question. All right. And so we are done with question 3. Wait. We are going to skip question 4 because I think we went through. It's for the children. This is a Laplace transform question. Yeah, we solved it yesterday. All right. So number 5, find the transfer function and the corresponding natural frequency and damping ratio for the following circuit, given that R is this, all this. So now when you look at the circuit very, very critically, you see that the R, the L, and the C are all in parallel. Since they are in parallel, that means this being in is the same being here, the same being here, and the same being here. So what's happening is that your being in is equal to being out, which implies that my being out over being in is 1. All right. Now we are supposed to find our natural frequency and damping ratio. Now, if this is our transfer function, which is written as, let's say our g of s equals 1 over 1, we know that our general form for second order systems, we have omega n squared over s squared plus 2 zeta omega ns plus omega n squared. This omega n squared is a constant. So we can say that since this is a constant, omega n squared is equal to 1. There's no s or s squared here, so it's just equal to the constant by which omega n squared. That our natural frequency is 1. Now, our 2 zeta omega n should be equal to 0 since there is no s component here, which means our damping ratio is 0. 0 means there's no decay. So yes, there's no damping in the system. All right. Right, so this is I'm doing this in conjunction with my boss here, Tamakloe. So from here on, you'll be hearing from him. He's going to take over and do our bold plot for us. Thank you very much.
Please, good evening. So please let's start from let's do the root locus first, number 7. Okay. So we'll come and do the code plot. So let's do the root locus. Okay. So please, anytime you are doing root locus, you have to follow a certain number of steps so that it will be easier for you. Okay, so even after you finish solving this question, make sure that you go through the steps a number of times so that you're familiar with it. Okay. So here the question says that sketch the root locus for the system with the following characteristic equation. So note that they've given us the characteristic equation, not the open looking. They've given us what they've given us is okay. What they've given us is our 1 plus kgh. That's what they're giving it to us to be 1 plus k going into s plus 2 over s plus 1, s plus 6, and then s plus 8. So first thing, find your number of poles. So if we check how many poles we have 1, 2, 3. We have 3 poles. How many zeros do we have? We have 1 0. That's what we have here. Okay. So now your step 1. Your step 1 is to find the number of branches. How do you know the number of branches? The number of branches is, so it's called number of branches or the loci. Okay. That one is specified by, you check your poles and your zeros. Which one is big? Like which one is the highest? Because you have more poles than zeros. So your loci takes the highest value. So you have 3 branches. Just for your okay, we'll see how it will come in. So first thing is to find your locus or your branches. The second step is to find your number of asymptotes. Okay. So if you check the question, we are answering the question. It says that clearly indicate the following part: number of zeros, number of poles, number of asymptotes, centroid of asymptotes. So we are finding all this. So our number of asymptotes is given by poles minus zeros, just like that. So we have 3 minus 1 is equal to 2. So this is the number of asymptotes we have. Now the next thing you find, see your asymptotes will span a certain angle. So the next thing you find will be the angle of asymptotes. Okay. So as I said, no matter the question you have, no matter how the question is, this is how you solve it. First one, loci. Second one, number of asymptotes. Third, angle of asymptotes. The angle of asymptotes is given by 2k plus 1 multiplying 180 over the number of asymptotes. In this case, let me say p minus z. So I'm getting 2k plus 1 times 180 over 2. Okay. Now, what is this k? This k is a set of whole numbers. So k is 0, 1, 2, 3 till infinity. That's k. This is what k is. So how do you know which case to use? Because our number of asymptotes is 0, our number of asymptotes is 2. It means we'll use k to be 0 and k to be 1. We'll use 2 k's. If number of asymptotes was to be 3, we'll use 0, 1, 2. So you're following? Yes. So it means that first, so we are putting in k 0, 1, 2 because our number of asymptotes is 2. If we had 3 asymptotes, we would have used 0, 1, 2. That is how make sense. If I'm not making sense, kindly ask your question in the chat. Oh, alright. Now when k is 0, what will I get for the angle? When k is 0, this place goes to 0. So I have 180 over 2, that's 90 degrees. Secondly, we'll do for when k is 1. When I put in k is equal to 1 here, I'll get 180 times 3 over 2, and that will give us 270 degrees. So the angle of my asymptotes are 90 degrees and 270 degrees. Now the fourth step is to find what we call the centroid. Okay. The centroid is where the asymptote will span from, will span out from. How do you find the centroid? You just sum the poles minus sum of the zeros and divide by the number of poles, b minus d. Okay, so someone is asking a question that how was the loci gotten to be 3? So I said that the loci or the number of branches. First, you calculate for your number of poles. In this case, I had 3 poles, right? And I had 1, 0. So you check. So the loci is equal to the maximum value between your poles and your zeros. So your loci is equal to, you compare. I have 3 zeros. I have 3 poles. I have 1, 0. 3 and 1, which one is big? 3. So your loci is equal to 3. That's all. I hope I've answered your question. Now the centroid is given by sum the poles. So here, the poles are what? You equate each of them to 0. So the poles are minus 1, minus 6, minus 8. Okay, we can see it here. The zeros are minus 2. So you sum the poles. So I'm getting minus 1 plus minus 6 plus minus 8 minus the zeros minus 2 all over poles minus zeros. So poles minus zeros is 2. We done that one at the top. So when you do this, you get minus 15 plus 3 minus 13 over 2. That will give you minus 6.5. So we have answered every question we're supposed to answer. Here, question says that clearly indicate number of zeros. We did that. 1. Number of poles. 3. We've done that. Number of asymptotes. We said it was poles minus zeros. 3 minus 1. 2. Centroid. We said the centroid, you sum the zeros, sum the poles, sum the zeros, subtract the zeros from the poles, and divide by the number of asymptotes. That's the p minus z. We've done that. Now, there's one thing for us to find. You have to find the breakaway point. You have to find the breakaway point. But before we find the breakaway point, usually after you find these things, you make a sketch. Okay, you do a rough sketch somewhere. Then after you find your breakaway point, you now come and do your original sketch. Okay. So, all right. So now you have to do a sketch following some rules. So So let's see how we can go about it. So I'm just doing my pole 0 plane. All right. So I'm having. So you just draw your poles and your zeros in the plane, okay? So I'm having at -1, I'm having a pole here. At -2, I'm having a 0. Okay. Then now at -6, I'm having another pole here. And then at -8, I'm having another pole here. So now we are done indicating our zeros and poles in the plane. Okay. Now, when you are done with this, what you have to do is that you have to start numbering. Okay, so you start from your right. This is my right. Right. So this is, you number the elements, you number the poles and zeros together. So this is my element 1, element 2, element 3, element 4. Now, one of the rules says that there's always a locus to the left of all numbered elements. So I'll check this element 1, right? So to its left here, there will be a root locus here. So I'll draw a line between them. This is an even number. So to the left of even numbers, there's no locus between them. So I'll go to the next odd number, that's 3. And then you draw a line to the left of 3. That's all. I'm saying this side again. You number the zeros and poles together from your right. So I have element 1, element 2, element 3, element 4. Then now you draw locus to the left of the odd numbers. This is 1. So to the left of 1, there'll be a locus. To the left of 3, there'll be a locus. Fantastic. That's one of the rules. The second rule is that, or another rule is that the locus always starts from zeros. Starts from poles. Sorry. It starts from poles and it terminates or it ends at zeros. Okay. So one thing I'm not mentioning yet is that the number of poles, let's say, must be equal to the number of zeros. Let's see. So initially I had the number of poles I said was equal to 3. My number of zeros was 1, right? Yes. This number of poles, we are talking about finite number of poles. Okay. So I have 3 finite number of poles and 1 finite zero. Now, at infinity, if you add the poles at infinity and the poles at 0, they must be the same. So it means at infinity, what do I have? I have 2 zeros at infinity and 0 poles at infinity. Am I making sense? It's just take it like this. I have 3 poles, 3 finite poles. I have 1 finite zero. They must be the same. How many must I add to the zeros to get the poles? 2. Which means there are 2 zeros at infinity. That's all. So there are some zeros at infinity somewhere in space. Okay. So now between this pole and this zero, they are joining. There's a locus between them. So I'll show an arrow like this. Because we say that the root locus starts from a pole and terminates on a 0. So I've done this. Okay. Now it's left with these 2. Now we know that for these 2, they will terminate at infinity. They will terminate at infinity. Okay. So let's see. Now let me identify where my asymptote is. When we calculated, we got the asymptote to be negative 6.5, which means our asymptote to be here. It is negative 7, our asymptote to be somewhere around here. So my asymptote to be here. The angle of your asymptote will be what? 90. You measure the angle from the positive real axis. So here. So 90 here. Then the next one was 270. So 90 and 270. Which means that my asymptote is, one of my asymptote to go up. My second asymptote will come down. But that we say we have 2 asymptotes, right? So one asymptote goes up, one asymptote comes down along the angles 90 and 1 and 270. Fantastic. Now, if you have 2 poles and you have a root locus between them, the root locus will come out from them. Because we say it comes out from them and end at poles. So it must come out from them and then it must go to the poles, right? But before we know the poles it will go to, we must calculate the break breakaway point or the breakout point. So now we can come and do the last part of the question that asks us to calculate the breakaway point. Okay. So how do I calculate the breakaway point? Let's see how we do that one. That part is a little some way, so kindly pay attention. Right. So I'm having it like this. Now we were given the characteristic equation to be 1 plus KS 1 plus KS plus 2 over S plus 1, S plus 6, S plus 8, like this. Right. So here's what you do. We are using 1 plus KGH. We'll use this equation. It's equal to 0. This is called the characteristic equation. We use this equation. Okay, so we'll equate this to 0. Because as I said, these are KGH. So this must be equal to 0. When you get here, you will make K the subject. So this is steps. As I said, if you are finding a breakaway point, here's what you do. First, 1 plus KGH is equal to 0. In the question, they give us that 1 plus KGH already as this. So we'll make K the subject here, which means K multiplying S plus 2 over S plus 1, S plus 6, S plus 8 will be equal to negative 1, right? So K will be equal to negative S plus 1 multiplying S plus 6 multiplying S plus 8 all over S plus 2. So this is my K. Okay. So I have to simplify this. So you multiply everything at the top there, and then when you simplify it, please take time and simplify. You get K to be equal to negative of S cubed plus 15S squared plus 62S plus 48. So please take time and simplify it. First, multiply these two, you get a quadratic, and then come and multiply by this one. So this over S plus 2. So what are we doing? We are making K the subject of this equation. 1 plus KG H is equal to 0. All right. Now, after you get your K, so let me clean this for now. So after you get your K, what do we want to find? We want to find the K, the S. That's what we'll find. We want to find the K, the S. Okay. Why do we do this? If you read the normal list, they say that the breakaway and the breaking points are turning points. And we know that from calculus, at the turning point, dy dx equals 0. The derivative at the turning point is equal to 0. So that's what we are applying here. So if you want to understand why we are doing this, that's why we are doing it. The breakaway and breaking point are turning points. And at turning point, derivative at turning point is equal to 0. So that's why we are doing this. All right. So let's move on. So if I find the K, the S, this is a quotient. So I'll do quotient rule. Quotient rule, if you have U over V, it becomes down times differentiate the top minus top times differentiate the down. If you say it in English, it's simpler. So I'll have down, right? So I'll have the down times differentiate the top. I'll get what? Don't forget there's a minus that I'm not bringing. Okay, let me bring it here. So 3s squared plus 30s plus 62 minus top times differentiate it down. If I differentiate it down, I'll get 1. I have it like this. So all over v squared here. So I'll do this and divide it by s plus 2 all squared. So now my decay ds, when you expand this one minus expand this multiply by 1, you get 2s cubed plus 21s squared plus 60s plus 76 all over s plus 2 all squared. So this is my decay ds. Then now we know that at the turning point, derivative is 0. So now we'll come and do decay ds is equal to 0. So we'll equate this function to 0. Okay. So we'll equate so we'll equate this fraction to be equal to 0. Okay, let's move on. Alright. When we do that, we'll get 2s cubed plus 21s squared plus 60s plus 76 over s plus 2 all squared is equal to 0. So this will give you cross multiply, you get 2s cubed plus 21s squared plus 60s plus 76 equal to 0. So 21s 2s cubed, sorry. When you get here, you do calculator work. You punch. So you get your first S1 value to be negative 6.98. Then you get S2 to be S2 is negative 1.76 plus 1.53J. You get S3 to be negative 1.76 minus 1.53J. So these are three values. And this is why it was paramount or expedient for us to make the rough sketch. See, in our rough sketch, we had this, there was a 0 here, right? Then we saw that there was another pole here, another pole here. So we know that our breakaway point will exist. Here was minus 6, here was minus 8. Our breakaway point will exist between minus 8 and minus 6. So among these values, you can see that yes, our S1 is actually between these two values. So now we can do what we are supposed to do. We can draw. So let's see. Let's make a very nice sketch here. Minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. We said that minus 1 was a pole, minus 2 was a 0, minus 6 was a pole, minus 8 was a pole. We said this is element number 1, so there will be a locus to its left. Element number 3, there will be a locus to its left too. So I have it like this. Now we know that there was a centroid here at negative 6.5. So our centroid moving at angles 90. So one asymptote, our asymptote to move along the centroid. So the first asymptote goes to angle 90. Second asymptote comes to angle 270. So we measure the angles this way, 90 and 270. I have it like this. Now we got our breakaway point. See, we got our breakaway point. We got our breakaway point to be negative 6.98, which means that I told you early on that the poles, the locus emerges from them. So it will come from here, it will also come from here, and they'll meet at a point. The point where they meet is the breakaway point, which we found to be negative 6.9. So it will be somewhere around there, very close to negative 7. So this is where the breakaway point is here, which means that this locus comes here, this locus comes here, and it meets, right? When they meet, they must move towards the infinite zeros. We said that we had two infinite zeros. And since the root locus is symmetrical, it means that there will be one zero up here and there will be one zero down here. So when they emerge here at this point, okay, when they meet and they are about to break away, one of them must be asymptotic, so it's go like this and go like this, and the other one to come like this, down here and come here. Let me make a neat sketch. Let me make a very neat sketch. I'll leave a wide gap between the minus 7 and 8 so that you see well. Okay, so we had it like this. Minus 1, minus 2, 0, pole. Root locus from pole to 0, done. Okay, let me see. I have minus 6 here. I have minus 8 here, right? Let's say I have minus 7 here. We got our centroid to be minus 6.5. One of our asymptotes is moving along the 90 degrees. The other one will move through 270 degrees. I have it like this. I got my breakaway point to be minus 6.98. You see that the root locus will emerge. It will come from the pole. So there's one pole here. There's another pole here. So it will come from here. Fine. It is moving in this direction. Get to this point. Move from here. Get to this point. Now, when it gets to this point, what happens to it? It must break away and go to the infinite zeros. And I'm saying that since the root locus is symmetric, it means that there's one zero here, there's another zero down here. So when they meet, one of them will move like this. It will move asymptotic to this one, to infinity. This one also moves to infinity. And there you have it. So this is how your final drawing will look like. So in answering the question, we ended up doing everything. We're supposed to find number of zeros, which we found. Then if you watch the online videos, the people said like he will make it something like this. Like he will say find number of finite poles, find number of infinite poles, find number of zeros. So once you see this, you can see that you can find number of poles. There are 3 poles. There's 1 0. And I'm saying that if you add the number of finite zeros, let me say it all. There are 3 poles and there's 1 0, right? Sure. They must be equal. They must be equal. So how many zeros will you add to 3? You add 2 zeros, which means that there are 2 zeros at infinity. It makes sense. So it means that here I have 3 finite poles, 1 finite zero, 2 infinite zeros, 0 infinite poles. How many asymptotes? We said that when you subtract number of poles, you do number of poles minus number of zeros. 3 minus 1, 2. Find the centroid. You sum the poles. So you do minus 1 plus minus 6 plus minus 8. Put it at one side. Sum the zeros. Here there's just 1 0, so minus 2. So you subtract the minus 2 from the sum of the poles and divide by number of asymptotes, in this case, which is 2. Now, this is that you must also find the angle of the asymptotes. Angle of asymptotes, which is given by, you do 2k plus 1 times 180 over the number of asymptotes, which is given by p minus z. And we said that you put in k 0, 1, 2, 3, 4, based on the number of asymptotes you have. Because we have 2 asymptotes, we put in k is equal to 0 and k is equal to 1. When you put k 0 into this, you get 90 degrees. When you put k is 1, you get 270 degrees. So that's what gave us this. Our centroid was here, minus 6.5. Our asymptote moves in 90. Second asymptote moves at 270. Then we go ahead to calculate our breakaway point. And I say that for our breakaway point, we will use this equation, the characteristic equation 1 plus kgh is equal to 0. Make k the subject here. You get a certain equation. Find the kds. You get something. When you find the kds, you do the kds is equal to 0 to find the values of s. And I'm saying that before you find the breakaway point, do a rough sketch so that you know, you have an idea about where your breakaway point should be. So that if you get 3 answers, you can see that, okay, from our rough sketch, our breakaway point is between negative 6 and 8. That's why we choose the negative 6.98. So that one comes here, which means that we know that the locus comes out of the pole. So it will come out and come out. So we show the arrow. Now they meet at a point and they break away. When they break away, one of them will go to the infinite zero here. The other one also goes to the infinite zero down here. And that's all for this week. So the steps is the steps. Please be familiar with the steps. Now go to the nominees and try some of the examples. See that once you have the steps, you can do a number of them. Now you must know that if we have same number of poles, for example, if I have something like this, let's say my kgh, my open loop transfer function, let's say is k s plus 2 s plus 4 over s plus 3 s minus 1. I have something like this, right? Here, let's go through the procedure. First one, our loci is the maximum of the number of poles and number of 0. So here there are 2 poles and 2 zeros. So my loci is 2. That's the first step. Second step, you find your number of asymptotes, which is p minus z. Here we can see that it will be 2 minus 2. That will give you 0. Which means that if you have equal number of poles and equal number of zeros, you will not have any asymptotes, which means that no centroid, which means that no angle of asymptotes. So when you go to the normal needs, you see a question like that, then you'll be able to solve it. Okay. So for something like that, usually you get something like this, and I think it always works. I think it always works. I'm not really sure, but in an example, in one example in normal needs, like they had the zeros here like this. Then they had not this question, please. They had the poles here like this, right? So we knew that okay, this is an odd element, so there will be a locus from here to here. This is element 3, so there will be a locus from here to here. We know that locus enter zeros and come out from poles. When they come out and they meet at a point, they will break away. Break away to where? Here, there's nothing at infinity. So when they break away, they must come to the zeros here. So when they break away, to come here. Break away here. This one also break away here. So that's how you go about something that will look like that. So please check the normal needs. You'll be able to do it. Just follow the steps. Loci, asymptote, centroid. Then here you have to find your breakaway point, which we know. Make here the subject from this. I'm saying this several times. Make here the subject, find the k, ds, equate this to 0, and find the values. So here, if you do it correctly, you see that you can get 2 answers. You get 2 answers. So from your rough sketch, you can now know the one that's your break-in point. Break-in means when they break away, where they arrive at. You can find your break-in point, also find your break-away point. Okay. So that's it. You can evaluate it. Yes. So that is how you go about the root locus. That's how you go about the root locus. Let me see. So the rules are here. All right. It's the same thing. So from what we've done, you can answer this question now. This question has 4 poles, 1 0. Right? This question has 4 poles and 1 0, which means it has 3 infinite zeros. So you just go through the procedure, find number of asymptotes. That's poles minus zeros. So 3 asymptotes. Find your centroid. So you find your centroid, find your angle. So when you go through the process, you will see how they came about this drawing. You see how they came about it. Your asymptotes will be, your angles will be 60 degrees, 180 and 300. So you can see that the first asymptote, second asymptote, and third asymptote. Then there are 2 poles here, so they will come out, meet at a point, and they will break away along the asymptote. So break away along the asymptote. Okay, so you can do this one too. If you can do that one, you can do this one too. Okay, so you can do it and then send answers to the class group for all of us to see how you're going about it. All right. So same thing here. So now we need how to find our breakaway and break-in point. We've done that one already. Then, so that's it. So that's how you go about this question. There's one last part about the imaginary axis. That one, so from what we've done, yeah, you'll be able to do it. Let me see. Let me just go to a new page and show you how. So yes, I was saying that if you want to find you see, in the last example I showed you normally, we saw that it looked like this, right? It looks something like this. This is how the loci look like. You can see that the locus is cutting the j omega axis. They can ask you to find the point at which it cuts the j omega axis, and that's what I'm talking about right now. So first, you use this equation 1 plus kgh, this same equation here, equal to 0. Use this equation here. or you don't even you just use the 1 plus kgh. Okay, then you solve, you simplify it. So let's say in this case we had 1 plus k s plus 2 over s plus 8 s plus 1 s plus 6, something like this. So you simplify this one, that is, you find LCM, cross multiply, and do everything you are supposed to do. Okay, so when you are done, so here like this, when you simplify that one, you see that you get something, you get an equation that has k in it. So you get s cubed plus 15s squared plus 62s plus 48 plus k into s plus 2. So this must be equal to 0, so that the denominator will go away. So in the end, you'll be left with this. Then when you get here, you use the Routh-Hurwitz that Aggrey spoke about. When you do that, it's just a similar concept as the example one you solved. So I'll not talk about that one. Right. So that's how you solve the number 7. Now the number 8. This is block reduction. Please, block reduction, we all have different ways of doing it. So I will not solve it. But then just a quick recap on the steps, on the basic steps, as a form of revision. So you must just know the rules. Yeah, the basic rules. Yeah. So we just talk about the basic rules. Okay. All right. Yes. Yeah. All right. So yeah, so we know that if we have two blocks in cascade like this, let's say G1 and G2, two blocks in series or in cascade, this is the first one. Then the overall transfer function is just their product, G1, G2 in one block. The second one, if you have two blocks in parallel, how do you see parallel? Let's say I have G1, G2. Parallel, they emanate from the same pickup point. So there's the same pickup point, they have the same pickup point, and they terminate at the same summing junction. Okay, and they move in the same direction. So be careful. Sometimes people confuse the parallel with the feedback. It is parallel. So if you want to see parallel, look for a pickup point. See if they are moving in the same direction. Yes, they are moving to a summing junction. Here can be plus. Let's say here will be plus or minus. So the resultant is G1 plus or minus G2. Be careful about what is here. Yes, I personally I usually make mistakes with that. So be very careful with that side. Plus or minus. So if it was a minus, it would have been minus. Here too, it can be anything. So here can also be plus or minus. It can be like this. Just that you will find their algebraic sum. That's all. The next step is a feedback. Feedback, this is how a feedback looks like. G coming to an output. Let's say R of S, C of S here. Then it comes back here again to another block H. Comes here. Here can be plus or minus. So feedback, the transfer function of feedback is a top over 1 plus or minus top and down, product of top and down. See, and I use the English language so that if I see that, I just know I'm talking to myself and I'll just do it straightforward. So you can also adapt that way of solving it. Okay. So top over 1 plus, from the forward part, so top over 1 plus or minus G. It becomes a plus if it's minus. So they are opposite, they contrast. If it's a negative feedback, the equation is plus. Positive is minus. All right. Now the next thing, if I have a block here, G1, okay, I have an input R of S, I have an output C of S, I have a pickoff point here, let's say M. So this is the fourth step. As I said, you just need 5 steps, 5 rules. If I'm here, if you want to move a pickoff point from after the block, it's after the block. The arrow is going like so, it's like it's after the block. So before the block, your G1 comes still, right? You have your C of S here, you have your R of S here. If you move it from here to here, you pass that line. You pass that line through G1. So there you have it. You pass the line through G1 because that's all. If it were to be here, if it were here and I was moving it to the other side, assuming the pickup point was here, and I was moving it here, I'll pass it through 1 over G1. So you can just learn that from after the block to before the block is G1. The other one is opposite. That's all. So that's why. So I don't add that to my steps because I know one. So let me move to the next step. The next rule. Why do I keep on saying steps? So the next rule is that if you have a block G1, you have a summing junction here. If you move a summing junction from after the block to before the block, so let's say I have my G1 here, I've now moved the summing junction here, right? The line that was suspending, that line, you pass that line through 1 over G1. So it is opposite of pickup point. So pickup point from after the block to before the block, you pass it through G1. From here to here is opposite. But for summing junction, from after the block to before the block is rather 1 over G1. And then from here to here will be, you pass that line through G1. So these are the 5 you have to know. Now, if you have a question, just know that there is always an easier step than what you think about at first when you see the question. So every question, if you see that you start thinking, just hold on, pause, and rethink. First, look out for series. If there's no series, go and look out for parallel in that order. Because if you start looking out for feedback, always feedbacks are easy to see. If you start looking out for feedbacks, your fractions become a lot. So first thing, so it's like it's in this order. First, check for series. There's no series. Check for parallel. There's no parallel. Is there a feedback? Or even no. Even don't even come to feedback yet. See if you can use these reduction methods to create a series or a parallel. If not, come to feedback. So feedback will be your last resort because of this fraction that you don't want to work with. Okay. So that's it. That's these 4 rules that you need. Mason's rule. Mason's rule, please. Mason's rule, talk about it. So you can see that just so that you can get time to revise on the root locus. I didn't do the boat plot. So tomorrow, around late morning, just 30 minutes for boat plot, and that's all. Mason sure you can. I'm sure you can go about it. Fine. That one is just rule. So tomorrow, around late morning. Yeah, around late morning. Let's say around 11, we'll look at the boat plot, and then that'll be all for control systems tutorials. It was nice having you guys. Nice you are all listening to the team. Papa we started and I'm ending. So as I said, if you have any example, you can just solve it and put it in the class group, the main class group, so that we all see it and we'll all analyze it together. Okay. All right. If you're not in KNUST, you're in other places such as Australia, we have views from Australia, Canada, and co. Kindly solve it and add it, send it to, email it to us. Our email is there. Just email it and then we'll check it for you. All right. Thank you very much once again. Please, no questions so far, so we'll call it. So the Mason shoe, a quick recap. Mason shoe, first thing, find your forward path. So here, you can see that how many forward paths are here. Forward, if you want to know number of forward paths, small number. Sorry. So forward path is just move from beginning to the end, following a single arrow. So first thing, find forward path gain. Second, you find your loop gains. Then you proceed. So tomorrow we'll do both plots. That'll be the main focus. So if in 30 minutes time we are done with both plot, then if you finish the both plot before 30 minutes, we'll look at the other one. Okay. All right. Have a wonderful evening. Do your revisions. The Lord be with you all. And God be with you. And be with me too. And God be with me too.